As you're familiar with substitution reactions, SN1 mechanism is a multi-step reaction, whereas the SN2 is a concerted reaction with only 5-membered of transition state. The 3-membered carbocation that will be generated in SN1 serves 3 purposes for us. First of all, the carbocation is generated from a bulky alkyl substrate. When a bulky alkyl substrate converts into a carbocation, it will always do rearrangements. So if you have a secondary carbocation and there is a possibility of forming a tertiary carbocation, you will see a hydride shift and the carbocation will rearrange from a secondary carbocation to a tertiary carbocation. The second piece of information that the carbocation gives us is that it is a Lewis acid. What is a Lewis acid? It is an electron deficient species. So if you have a carbocation, what is going to attack on it? An electron rich species. So whatever nucleophile, charged or neutral, does not matter. If you have a charged nucleophile, it will be a stronger nucleophile. If you have a neutral nucleophile, it would be a weak nucleophile. So the nucleophile or the electron-rich material will attack on this carbocationic site. The third piece of information that the carbocation gives us is that it is sp2 hybridized. What does that mean? If your carbocation can generate a stereoisomer, this carbocation will be a planar molecule or a planar geometry because of its sp2 hybridization. It is a flat molecule. So the nucleophile has a 50% chance of attacking from one side or from the other side, resulting in 50% R enantiomer and 50% S enantiomer, which is nothing but racemic mixtures. Because this carbocation and SN1, we will see different kinds of products being formed. Looking at our particular experiment, the first step, which is the rate determining step, formation of carbocation, the leaving group, leaving determines how fast or slow the overall reaction would be, and hence it is labeled as the rate determining step. Whenever you have a leaving group, so you have this substrate, you scan the molecule for vulnerable sites or a polar bond, and you see that this is the polar bond where the substitution can happen. But looking at OH is a bad leaving group. What defines a good leaving group? A weak base is a good leaving group. So OH being a strong base is a bad leaving group. So the first step is to ionize or protonate this OH by a proton transfer to make it a good leaving group. So proton from your solution, the HCl, will protonate our OH group, converting it into a water kind of a leaving group. Water is a weak base and a very good leaving group because it can exist independently. So once you have created a good leaving group, the first step is considered as the leaving group leaving and the flat planar sp2 hybridized carbocation getting formed. This Lewis acid or the carbocation that has been generated will be attacked by the nucleophile. So within our system, we have the proton as well as the nucleophile also. The nucleophilic attack on the electrophilic carbocation or the electron deficient site will result in a 50-50 chance of attack from forward and backward direction. Now we cannot label this molecule as a racemic mixture because you see this carbon is not chiral. There are two similar groups on this same carbon. Once you have recognized that a given chemical reaction is SN1 in nature, you will be expected to draw the products of that reaction. So we have seen that this substrate is primary substrate, which should have been an SN2 reaction. And what you have on hand is not a very strong nucleophile. You have an average nucleophilic structure. But what you do have is a protic solvent. A protic solvent is the one which can give away protons. For example, ethanol, ammonia, or any kind of amines, or any kind of alcohols. They are your protic solvents, water, HBr, etc. Now, when you have this situation that you have a protic condition, you know that you are going to have SN1 reaction. The first step would be the formation of carbocation. And what do carbocations do? The carbocation will rearrange. Right now, the carbocation is primary. Can it become secondary? Yes, it can. And so it is going to jump right here. So from a primary carbocation, it can jump to a secondary carbocation. If this molecule has still time, it will observe that there is a possibility of becoming a tertiary carbocation as well. And this is where you're going to see your hydride shifts. When you see your hydride shift, so there is this methyl group which is still on the carbon, but our molecule is no longer a secondary carbocation. It has now become a tertiary carbocation. Remember, the smaller groups will move first. Now the bromide will attack, and we are going to get a rearranged product. Anytime you have a carbocation, you will get rearranged products. So for our example B also, we are going to see some rearrangements. Why? Because of the protic conditions. Now in this particular system, when the OH will become your OH2, the first carbocation will form at a secondary location, this carbon, when the water molecule will leave. At this point, the molecule scans its surroundings. and observes that it can become a tertiary carbocation. Now both of these groups are same, so one of the methyl shifts and we get a methyl shifted carbocation. On this, the nucleophile, and what is the nucleophile right here? The cyanide ion will attack. Remember, carbocation is a flat molecule. It will attack 50% chance from top, 50% chance from behind. So this is the product that we are going to get from this substrate. I have shown a wavy line here. It is neither the wedged bond, neither the dashed bond. It can be in the front or at the back. So 50-50% chances for that.